Are we on? Okay, thank you. Yeah, okay, so today I'm going to be talking about another divide and conquer algorithm, a little bit more sophisticated than what we've seen. It's related to the integer, fast integer multiplication algorithm, but this is for matrix multiplication. And so the problem is that we have two matrices of size n by n, so they're both square matrices, n by n, n by n. We call the first one A and the second one B, and we want to multiply them to form C. So you all know how to do matrix multiplication. You've done it in numerous classes. You know the basic definition. And let's look at that first before we go any further. So let's just take a look at a 2 by 2. We have entry C11, C12, C21, C22, A11, A12, A21, A22, B11, B12, B22, oops, getting sloppy, B21, B22. Okay. So in a 2 by 2 matrix, let's look at the entry C11. C11 is A11 times B11 plus A12 times B21. So C11 is equal to A11 B11 plus A12 B21. Okay? So we have two scalar multiplications of the actual individual numbers. Multiplication here, and one addition. So that's for a 2 by 2. If we talk about an n by n, then each row has n entries, and to get the first entry here, which is still C11, to get C11 now, we have to multiply all the individual values in row 1 of A times each individual value here gets multiplied by a corresponding individual value in row 1, in column 1 in B. So this one gets multiplied by that, the second one gets multiplied by the second one in the column, the third by the third, and so on. And those individual products, those scalar products, are added together. So for an individual entry, C11 requires n multiplications and n minus 1 additions. Okay? And that's for a single entry. And in an n by n matrix, we have n squared entries. And so this implies that we actually do n cubed operations, n cubed multiplications and roughly n cubed additions. Okay, so how are we doing on the board there? That's good. Okay, now we'd like to have a method that is faster than that does fewer scalar multiplications and fewer additions. And I think before people saw how this was possible, people sort of felt that wasn't going to be, that was impossible. That the definition of multiplication, matrix multiplication, was just so embedded with this particular method, you can call this an algorithm if you like, that the whole definition of a matrix multiplication was so wedded to this particular definition, algorithmic definition, which clearly takes n cubed operations, that people couldn't imagine that it was going to be possible to do fewer operations. But if you just think of matrix multiplication as a function that takes in two matrices and produces a third matrix, then you can always ask, is it possible to produce that function, compute that function, in a way that's better than this particular definition of that function, this particular algorithm of that function. And this was possible, this was shown to be possible initially by a method due to Strassen. So this is Strassen's matrix multiplication. Okay, And Strassen's method is a divide and conquer. So we've seen divide and conquer. This is yet another one, a very interesting one, where we're going to think of submatrices and multiplying submatrices. Okay? So the division here is a division into 4 submatrices. So this is, again, now this is an n by n, so this is very large, not just 2 by 2. And so the submatrix here, which is n over 2 by n over 2 in size, we'll call this capital A11, capital A12, capital A21, capital A, oh, I don't want that to be A, excuse me. This is C. This is C11, C12, C21, and C22. Here is A11, A12, A21, A22, and then B11, B12, B21, B22. Okay, so we now have divided up the matrices and given names to each of the quadrants. And now note that C11, for example, is equal to A11 times B11 plus A12 times B21. Okay? Where here, this is a matrix multiplication. This is a multiplication of 2 matrices that are of size n over 2 by n over 2, n over 2 by n over 2. And so when you do this matrix multiplication, you get a matrix of size n over 2 by n over 2, or the dimension. And similarly, here is a matrix multiplication. And we all know what matrix multiplication is. So this is well defined. And you get, again, some result here, which is n over 2 by n over 2. Now, when you add 2 matrices, let me replace this by its result, or I guess I can just erase one of these. This now represents the result, A11 times B11. That's a matrix of dimension n over 2 by n over 2. When I add 2 matrices of the same dimensions, then what it means to do is just add the corresponding elements. Okay? The element here in the upper left-hand corner is added to the element here in the upper left-hand corner, and that, therefore, is equal to the element here in the upper left-hand corner. Okay? The next element over is added to the next element over, and that result is that element there in C. Okay? So you can think of C11 as the matrix multiplication of these 2 submatrices and the matrix multiplication of these 2 submatrices, and then the direct addition of corresponding elements create an n over 2 by n over 2 submatrix, which is C11. Now you have to kind of convince yourself that the correct thing is happening here. When I do this matrix multiplication, it's these elements times these elements, okay, and those are then added up and so on, and then these elements times these elements, and those are added up, and then those 2 are added. But that's exactly the same thing as doing the multiplication of this entire row by this entire column, and then doing the additions. Okay, so this works out. This you should feel comfortable with this. And similarly, we can describe C12 that way, C21 that way, C22 that way. So certainly, there's a divide and conquer and recursive way of talking about normal matrix multiplication here in this kind of notation. So, and then finally, at the base case, because this is dividing and conquering, we're going to, when we do this recursively, when I want to multiply A11 times B11, how do I do that? By the same kind of recursive division. Ultimately, we're going to get down to a case of Well, you can either think of it as a 2 by 2 times 2 by 2, okay, or you could think of it as a 1 by 1, which is just a single number, 1 by 1 times a 1 by 1, all right. Ultimately, we get down to individual scalar numbers in the dividing when we're doing the divisions, the recursive divisions. Okay, so we have a recursive dividing kind of algorithm. It gets down to finally individual numbers that you multiply together, and then we all know how to implement recursion, and therefore how this would work recursively. Now, how many scalar multiplications does this approach take? How many multiplications of individual numbers are implied by this kind of recursive divide and conquer? So we'll set this up. We'll set up the analysis by recurrence relation, by recurrences, which is something we've become comfortable with. Okay. Just have to find the right page in my notes. Okay, so we'll define T of n to be equal to the number of operations, and these are multiplications and additions, operations on individual numbers, number of operations to multiply two n by n matrices using divide and conquer. Okay? Well, okay, T of n, what do we have? Well, oh, I erased it. That's unfortunate. Let me put this back. C11 is equal to A11, A11, B11, B11 plus A12, B21. Okay, so recursively, yeah, we have two multiplications here of submatrices of size n over 2, okay, and one addition, okay. Well, we'll get to the addition in a minute. But this 2, that's for a particular submatrix C11. And we have 4 submatrices here. So when we want to multiply two n by n matrices, the divide and conquer, the division, really implies that we're going to do 8 multiplications of submatrices of n over 2 by n over 2. Okay? Now, for each one of the 4 of the resulting submatrices, we have to add 2 matrices together, which are of dimension n over 2 by n over 2. Okay? N over 2 by n over 2. And as we said earlier, what that involves is you take each element here adds together with a corresponding element in the same position over there. Each one only adds to one other, but every one adds to exactly one other. So how many elements are there in here? It's n squared over 4, the total number of elements. So n squared over 4 additions are done for this particular subarray, and we have 4 subarrays, so 4n squared over 4, which means n squared, okay? In my notes, this was 4n squared as opposed to n squared, but it's not going to matter. This is just a constant here anyway. The n squared is the critical thing. So we're doing something proportional to n squared. Did I make a mistake here in canceling these four? Let's just go over that again. So for each one of the n over 2 by n over 2 submatrices, we have to do an addition of these two submatrices, and that involves n over 2 times n over 2 individual elements. But that's n squared over 4, and then we have 4 of these, so yeah, n squared. But as I said, even if this was 4n squared, you'll see in a minute that's not going to matter for the analysis. Okay, so this is the total number of operations. And let me just point out, this is, well, this is a non-recursive part of this recurrence. This is the recursive part. Okay, now what does this solve to? Okay, we could unwrap this and figure out what we have for a closed form solution of t of n. And by the way, t of 1 is equal to 0, so that's the base case of this recursion. But if you remember from the master method, we don't even need particularly to look at the base case. And the master method already incorporates what would happen if you unwrapped. It's just a more formal version of that. And remember, in the master method, what happens, now let me just write out the general form of that. That's t of n is equal to a tn over b plus some function of n. So this is the general version of the divide and conquer recursion that's treated in the master method. And if you remember, the critical thing that you do in the master method is you form n to the log base b of a, and then you subtract a little epsilon there, and you want to compare that to f of n. Okay? So we're going to look in a minute at this particular one. How does this compare to f of n? So let's, bad board work, but let's go over here. So we have n to the log base 2 of 8, okay, and as opposed to as opposed to f of n, which is n squared, and this is minus epsilon. And we can see that for some epsilon bigger than 0, this is true. N squared is big O of n to the log base 2 of 8, because that's 3 minus epsilon. Okay. It looks like the framing is a little bit off. Can you shift it a bit so we? Yeah. Okay. Thank you. N squared is big O of n to the log base 2 of 8 minus epsilon for some epsilon bigger than 0. So n squared is big O of n cubed minus epsilon. And by rule, and this is for epsilon bigger than 0, by rule 1 of the master method, this implies that t of n is equal to theta of n to the log base 2 of 8, which means theta of n cubed. Good. So we've done the, we started out with the definition of matrix multiplication, which used theta of n cubed operations, okay? And we now have a fancier algorithm, divide and conquer, which uses recursion and ends up with a time bound of n cubed. So, no progress there. Okay, started out with n cubed, we're back to n cubed, so we obviously didn't do anything of importance. But what we did do is set up the framework and the analysis for what we will eventually do. Because what we really want to do is here, instead of this 8, what we want is 7. Okay? So we want a method which will only use 7 multiplications instead of 8 in this portion of the recursion. And here, it's not going to matter what this constant is. It'll turn out that the constant is going to be 18 in the method that I'll show you, but it won't matter. If you take a look at this recursion, t of n is equal to 7t of n over 2 plus 18n squared. Then we look at log base b of a minus epsilon compared to fn. Over here, let's go back. Then we'd be talking about, according in the master method, is n squared big O of log base 2 of 7 minus epsilon. Well, log base 2 of 7 is somewhere around 2.8. Okay? So let's see. Can you just pull back a little bit on the framing? Hello? Can you pull back a little bit on the framing so we're sure to see the whole board? Okay. No, don't pull in. Go back so I can see the whole. I want to see it from here to here. Yeah, good. Thanks. Okay. So now, okay, where was I? Yeah, n to the log base 2 of 7 is bigger than n squared. It's about n to the 2.8. So we have room for the epsilon. So n squared is big O of n to the log base 2 of 7, which means that 2.8 minus epsilon. Okay, that means that t of n in this case would be n to the log base 2 of 7, which is about n to the 2.81. Okay, so this is just setting up what we want. It's like the wish list. What we want is that in this recurrence, we replace the 8 by a 7. And what that means is that I have to show you a method that can do this kind of dividing and multiplication using only 7 multiplications as opposed to 8. All right, so let me show you how to do that. It was done by Strassen. Strassen was the one who showed how you could use just 7 multiplications as opposed to 8. Now, the only way I can show you how to do this is effectively by magic. I can show you it. I can't tell you how Strassen came to understand that or came to discover it. It just doesn't, I can't do a derivation of this. But what Strassen did, oh, and I'm going to be explaining this in a 2x2. So explain first Strassen's method in a 2x2 matrix, or 2x2 matrices. Okay? So the normal 2x2 multiplication would be 8 multiplications, 8 scalar multiplications, C1 times, A11 times B11, A2, etc. There would be 8 total scalar multiplications. And I'm going to show you how to do it with 7 total scalar multiplications and 18 additions, but we'll see, we've seen in the recursion that 18 is not really harmful. Okay. Now, what Strassen showed is that first, in Strassen's method, we're going to do some arithmetic that doesn't at first seem related to the matrix multiplication. It doesn't seem at first related to multiplying these two matrices. And of course, we're going to have to count those particular operations when I say that there's 7 multiplications. So Strassen's method first computes x1 defined to be equal to A11 plus A22 times B11 plus B22. Okay, well, one multiplication, two additions, one multiplication. Okay? X2 is equal to A21 plus A22 times B11. And I'm only going to do 4 of these because that's going to be enough to illustrate what I want, times B12 minus B22. Okay, so X3 is A11 times B12 minus B22. And then X4, hopefully everybody can read this, X4 is equal to A22 times B21 minus B11. Okay? And in Strassen's method, there are actually 7 of these. So there's an X5, X6, X7. Each one of these only involves a single multiplication. So these X values can be calculated with 7 multiplications and some number of additions and subtractions. It's less than 18. We're going to have some additional additions and subtractions in a minute, but we won't have any more multiplications. So at the beginning of Strassen's method, you just compute these 7 X values, each of which has a single multiplication, involves a single multiplication. Okay. Now, it turns out that we can use these 7 X values to calculate individual C values, C11, C12, C21, C22. And let me just show you one of those. And verify that it works. Okay? So, according to Strassen's method, C21 is equal to X2 plus X4. All right? Well, let's verify that. X2, according to this, is A21 plus A22 times B11. Okay? And X4 is A22 times B21 minus B11. Okay? All right, the A22, B11, A22 minus B11 cancel. And what we're left with is A21, B11 plus A22, B21. Well, what is that? That's A21 times B11 plus A22 times B22. That's exactly equal to C21. C21. So we have verified that that Strassen's method of adding X2 plus X4 to get C21 is correct. Okay? Now just illustrate, I'll write one more just to kind of give you an illustration. We won't verify it, but just to show you that the others are similar in nature. So C11 is equal to X1 plus X4, which we've seen. We know what X1 and X4 is, minus X5, which I didn't show you, plus X7. Okay, so these two you don't know what they are, but they're similar in form to the X's that you have seen, and they involve one multiplication only. And then we have some 3 additional operations, 2 additions and 1 subtraction. So C11 is of the similar form, and so on. And now, let me just say one thing. In this class, we're using the Kleinberg and Tardish book. It does not discuss Strassen's matrix multiplication method. However, the the book that had been previously used for this class, Corman, Lysis, and Revest Stein, does cover in detail Strassen's matrix multiplication. So you can look there and see what the particular x values are and what the particular uses of them are to get the c values. So you can look at the individual details, and just as we verified that C21 was correct, you can verify each of the other, and there are only 4 of them, so there are only 3 left for you to do. It's just kind of tedious in a classroom setting to verify it, and as I said, when you look at those details, you can verify those for yourself. Okay. Strassen's matrix multiplication method is also covered in other algorithm books that I know of. I learned it first in a book by Sarah Baaz. It's in a book by, forgetting his name. At any rate, it's in many algorithms books, and I suspect, I'm virtually certain, if you looked on Wikipedia, you would find the details there as well. So you can verify for yourself all these particular rules. It'll take you another 10 minutes. Okay, but I've shown you enough that you see the spirit of it and the nature of it. Now, it turns out that, well, forming the x's involves 7 multiplications, and forming doing all the additions and subtractions, well, we have some number of additions and subtractions here, we have some more additions and subtractions here, and it turns out that it involves 18 additions and subtractions. So Strassen's method for multiplying two 2-by-2 matrices uses 7 multiplications of individual numbers and 18 addition subtraction operations. Okay? Now, if you just wanted to multiply 2 2-by-2 matrices, this is no great improvement. That's not improvement at all, because 7 multiplications and 18 additions as compared to 8 multiplications and 7 additions in the method that comes with the definition of matrix multiplication. Obviously, Strassen's method is in fact slower. Okay, but we're talking in this class about what happens asymptotically, what happens when n gets big. All right, so let's go to some bigger n. But recursively, we're going to use the same idea. Okay, so back over to here in the divide and conquer, in the recursion that was set up, we have a submatrix A11 times B11 and a submatrix A12 times B12 equal to C11. And the similar, we can similarly write it out what C12 and C21 and so on are. Now we're going to use the same template, the same ideas that were in Strassen in multiplying 2-by-2 matrices. We're going to use those in multiplying higher dimensional matrices, n-by-n matrices. So if you think of this capital A11 as the little a11 and the capital B11 as the little b11 and so on, then you can use the rules under Strassen to do these operations. So you would form now a submatrix X1, which is the addition of the submatrix capital A11 plus capital A22, multiplied by the submatrix A11 added together with, B11 added together with B22. Okay? I'll try to write that down. Let me, well, I'll erase this. So now we have a capital X1 is equal to A11 plus A22, okay, multiplied by B11 plus B22. Okay? So this is a addition of matrices, and we know what that means. This is addition of matrices, is the multiplication of matrices, and so on. And we can use exactly the same ideas that Strassen used in talking about 2 by 2 multiplication. We can use those for n by n multiplication. Now, there is a point that's made in the expositions of this method that is, I never understood why it was really necessary. I mean, I understand mathematically why it was necessary. I never understood in terms of the exposition why you even had to point this out. But most expositions at this point say, notice that Strassen's 2 by 2 method never exploits the commutativity of multiplication of individual numbers, multiplication of scalar numbers. Okay? A times B is equal to B times A. That's commutativity. And if I'm talking about individual numbers, that's true. If I'm talking about matrices, however, even if they're both square, capital A times capital B is not the same as capital B times capital A. Even if when they're square, both of those are defined, but they're not the same result. Okay, so when the method goes from multiplying 2 by 2s and is used, the same method is used for multiplying larger matrices, you have to, well, the expositions say, notice that commutativity was never used here, okay, and well, okay, and therefore it's okay to use the same ideas when you're talking about matrices of higher dimension. To me, you know, it's just sort of obvious that if you do the same thing on matrices of higher dimension as is laid out here, it works for them. Okay, but maybe I'm missing a subtle point, and I just wanted to mention that to you. Okay, so we can use the same idea recursively for matrices of higher dimension, and we will get ultimately the right matrix. We will, even if this is an n by n problem, if we recursively break up each of the matrices and then recursively break them up, etc., and use Strassen's approach for doing those matrix multiplications, we will ultimately get the right result, matrix C. Okay. Maybe you have to think about that a little bit in the comfort of your own mind in some quiet moment, but I think you'll all see that it works. Okay. So let's do the time analysis again. So now, previously we had set up a recursion that's a recurrence was talking about the total number of operations. And now I want to divide it up into the number of multiplications that are done, and do an analysis for that, and then do another analysis just for the number of additions and subtractions. Okay, so for multiplications, what do we have? Let me get some notes here so I don't get lost. Okay, just to make things a little bit annoying, we're going to do the analysis n equals 2 to the k for some k. So I should have mentioned this earlier, because in the recursion we're dividing a matrix that's n by n into these pieces that are n over 2 by n over 2, and then we're going to do that successively and so on. So it's convenient, it would be convenient if n is a power of 2. it just makes everything work out nicely. And when n is not a power of 2, we can talk about how to pad the matrix or what to do in the recursion to handle that. But to first get the idea, it's just useful to look at a cleaner case where n is equal to a power of 2. So n is equal to 2 to the k for some k, and therefore we can define mk is defined as the number of multiplications, scalar multiplications, multiplications of individual numbers, number of multiplications used to multiply to 2 to the k by 2 to the k matrices. Okay? So in that case, mk is equal to, well, we know we have 7 multiplications of matrices that are now n over 2 by n over 2, dimension n over 2 by n over 2, which means their dimensions 2 to the k minus 1 times 2 to the k minus 1. Okay? So mk is equal to 7 m k minus 1. So this is just counting the number of multiplications in the Strassen approach to multiplying two large matrices, matrices of 2 to the k by 2 to the k. We get this recursion mk is equal to 7 because we're multiplying 7 matrices of dimension 2 to the k minus 1. Here's one by 2 to the k minus 1 times another one of that same dimension. So we have 7 k minus 1. And ultimately m0 is equal to 0. Okay? Well, what does this solve to? All right? Just think about this unwrapping. I mean, you could use the master method or something, but just unwrap this thing. Okay, we have 7 times whatever this is, which is 7 times m to the k minus m times k minus 2, etc. So this is ultimately equal 7 to the k. 7 to the k. Okay? So 7 times 7 times 7, unwrapping this thing until we get down to 0, and we're obviously going to do that k times. Well, k is log base 2 of n, so that's equal to 7 to the log base 2 of n. Okay? This is a little clumsy, but you all remember the trick that we've talked about. We can exchange the 7 and the n here. So this is equal to n to the log base 2 of 7. And that's about n to the 2.81. Okay? So that's the analysis of the number of scalar multiplications. It was done separate from the analysis of the number of additions and subtractions. So now we'll do that. So number of additions and subtractions, well, I said over here, the 2 by 2 uses 7 multiplications and 18 additions and subtractions. Now what happens when you use that recursively? Okay. So let's get some notation. Let P of k equal, define as the number of additions and subtractions done to multiply to 2 to the k by 2 to the k matrices. Okay? And set up the recursion for that. Well, first of all, P1 is equal to, this is now the 2 by 2 case, so we know how many additions that is. That's equal to 18. Okay? Now for k greater than or equal to 1, sorry, greater than 1, okay, we are, well, let me just let me show you what it is, and then I'll try to explain it a little bit better. P to k is equal to 18 to k minus 1 squared plus 7 pk minus 1. Okay, well, where does this come from? Well, we know that the Strassen's method for multiplying 2 by 2 matrices uses 7 multiplications and 8 fractions. But now when we're talking about two matrices that are of dimension 2 to the k minus 1 times 2 to the k minus 1, when we're adding those together, okay, when we're adding two matrices that are of those dimensions, how many individual scalar additions are actually happening there? It's 2 to the k minus 1 squared individual additions that are happening there. And according to Strassen's method, we're going to have to do 18 of those operations on matrices of this size. Let's just go back over to here. We're looking at C11, looks like that times that, so that when I'm adding these two, this matrix plus this matrix, and these are n over 2 by n over 2, then the number of additions here is n squared over 4. And that's really what's happening here, because in Strassen's method, you have to do 18 of those kinds of additions or subtractions of matrices of this dimension. So we've got that, operations on individual. And remember, again, in Strassen's method, this addition part was not recursive. We're not talking about something that's happening recursively. We're talking about something which is done on a matrix of that dimension, 18 of those. However, in Strassen's method, we're doing 7 recursive calls to matrix multiplication. Okay, so on a 2 to the k times 2 to the k, we're going to do 7 recursive multiplications, and those involve some amount of additions and subtractions. When you multiply two matrices of some dimensions, the method requires p times k minus 1 additions and subtractions. And since there are 7 multiplications that are required, recursive multiplications that are required on matrices of dimension 2 to the k minus 1 times 2 to the k minus 1, we have to have this term in the recursion that's talking about how many additions we do. So this is the recurrence that's relevant to understand how many additions are done. P of 1 is equal to 18. Pk is equal to this. Okay, now, how do we solve this? I got myself painted in a little bit of a corner here by using these k's. I'm not really sure why I ended up using k's, just because I wrote them out in my notes this way. I could have probably started just used n all the way through, and then instead of 2 to the k minus 1, it would have been n over 2. This would have been pn 18 n over 2, etc. But I did it in k's, and but in solving this, now I'm coming back to this to say that this is really the same as p of n is equal to 7 p of n over 2 plus something that is on the order of n squared. Okay? So this, since 2 to the k minus 1 is n over 2, so we have n over 2 squared is on the order of n squared times 18. So it's really 18 n squared over 4 it's on the order of n squared. So we have this recurrence, and we've just looked at that earlier. This on the order is really the same as putting a constant here, c. But when you use the method, this constant didn't matter. We did this whole analysis earlier. I've erased it. Is it over there? No. Well, let's just do this one last time using the master method on that recurrence. So master on that recurrence using rule 1. Again, we're going to form log base 2 of 7, n to the log base 2 of 7 minus epsilon, and we're going to compare that to n squared, and we're going to see that n squared is big O of log base 2 of 7 minus epsilon, and that implies that P of n in this case is equal to theta of n to the 2.81. Okay. You can do a better analysis and bring this down a little bit. I'm not going to show you that. Let me just say well, for one thing, we've done the analysis now for a number of additions and for a number of multiplications. Both of them are n to the 2.81. That's real money when n is big as compared to n cubed. Now, there need additional ideas to make this method practical, especially in comparison to sparse matrix multiplication. But people have actually done that for some real applications, and n now can be very, very large. When Strassen first invented this, people weren't multiplying huge matrices, but they are today. And so these ideas really have some meaning in addition to the theoretical jolt that people got when they realized that no, n cubed wasn't necessary. You really could do better. And today, there are methods, I think, that get down to about n to the they're below n to the 2.4. So from n to the 2.81 to something now south of n to the 2.4, there are methods like that. And they just get more complicated and more clever, and I have no idea how people invent them, what principles they follow to get there, or they just get there by fiddling and being smart. Okay, good. This fit into one lecture, and I won't have to continue with this next time. All right, thank you.